this is kind of a talk in misplaced hobbies. I got nerd sniped at work. Does everybody know what nerd sniping is? So I got nerd sniped at work where we were talking about DNSs, and it turns out I didn't know at the time what a DNS did, other than like, it's a thing, it makes the internet go. So I decided that the obvious way to learn what a DNS was to write my own, and obviously it had to be completely useless, because why make anything useful? So let's talk about cats. I'm Monica, hi. For conversation starters later, ask me how a taxi driver taught me how to cook a lobster. I work for Google, I work on Chrome, which actually means I'm a C++ developer, and I'm only kind of posing as a Node developer here, because I wrote 90 lines in Node once. And I'm from Canada, so I'm going to say sorry a lot. I'm already sorry about that. Yeah. So let's talk about DNS instead. So DNS stands for Domain Name System, and it's basically a giant phone book for the internet. Every time you see a URL that your brain can parse, that's not actually a thing. The thing that you're looking at lives at an IP, so the DNS is there to translate this human-readable URL into an IP that's actually useful and points to a resource. That's what it does. So cat DNS is a thing that I wrote that also translates a human-readable URL into something, but that something is cats, and it's always cats. And those cats are a service written in Go by my coworker named Cat. I'm not even joking about that. And it's basically a web service. It lives at a static IP, and every time you try to go to any URL, you go to that, and you get a random cat from Reddit. Except for this cat, which is hard-coded to show up every like 15 cats, because it's kind of amazing. The server is written in Go, but the actual DNS part is written in Node, and it's kind of hilarious. And I'm going to tell you everything about DNS that you ever need to know, and then show you 3 slides about Node. That's that talk. So if we want to write a DNS system, we need to understand a couple of things. First, how does your browser talk to a DNS server? What sort of magic shenanigans happen in this DNS server to actually find the right IP that you're looking for? And maybe if there's any tools that could help us with this so that we don't have to read the RFC. We'll get to that in a second. So your browser talks to a DNS server over UDP. UDP stands for User Datagram Protocol, and it's kind of like TCP/IP, only it's really, really simple and really easy to implement. Somebody on Reddit called it the honey badger of internet protocols, and that's because UDP does not give a shit about anything. It doesn't have state, so every message is new. It doesn't care that you've told it something else before. You have to like tell it the same thing over and over again. UDP remembers nothing. It doesn't need to know who you are, so it has no authentication, it has no handshaking. Everybody can talk to UDP. UDP is really friendly. UDP is also really rude because it doesn't care if you got its message. So you're going to ask it a question, it's going to give you back an answer. I don't care if you got it. You just got to ask again if you didn't. So that's UDP. The reason why we really love it for DNS is because a DNS server is really, really, really chatty. So remember, I told you at the beginning that every time you see a URL that your brain can parse, that's not a thing, and you have to talk to a DNS server to resolve it. This means that if you write the simplest HTML page, you're going to include jQuery, of course, so that's a DNS request. And you're probably going to shove some CSS resources in there, so that's a DNS request. And imagine if you're going to like images.google.com, for every image, you're going to have to probably do a DNS request. So DNSs do a lot of talking. This is why UDP is great, because it's really fast and they don't have time to do any polite conversation with your browser. Google has a public DNS, lives at 8888, and you can use it to configure it in case your ISP's DNS, we'll talk about that in a second too, is really crappy. But it came out around 2012, and then they published some numbers, and they're kind of hilariously scary. So at the beginning, and this was 2 years ago, so I'm sure it's much worse now, they were getting something like 800,000 requests a second to a glorious total of 70 billion requests a day. That's not one machine, that's a cluster of machines. But this is the sort of conversation and sort of busyness that a DNS server has. And this is why you want it to be really fast. The Google DNS replies in about, on average, on 45 milliseconds. Most of the time it's much faster than that because it gets to cache a whole bunch of questions. But if it has to go and fetch a whole bunch of things for you, it's going to take about 45 milliseconds. Bragging time, everybody. Cat DNS responds in 7 milliseconds, blazing fast. Keep in mind, it only knows one URL, one IP, though, and that is cats. So, you know, it's really fast for what it's good at. Also because it does nothing. All right, so let's talk about DNS and how it works. At the top level, does this slide show up? Yeah, perfect. At the top level of the entire conversation, you have your browser, and when you're asking for a URL, like images.google.com, you're going to hit a DNS. And this DNS is going to respond with 2 things. It's going to echo back your question so that you know you're getting the right answer, because your browser is probably going to make like 50 different DNS requests at a time. And then it's going to give you 2 pieces of information for that URL. It's going to give you the TTL, and I'll go into painful details about that later because it's a pain in the ass, and the IP of that resource. That's all it does. 2 pieces of information, really small message. So the way this actually works is that this first DNS system server that you're hitting, it's actually called a recursive name server. And if you haven't ever configured it on your router or on your computer, that comes from your ISP. So every ISP hosts their own DNS. Sometimes it's just a plain out-of-the-box port of bind, which is an open-source DNS. And the thing about recursive name servers is they don't actually know where anything lives. They can't actually do any resolving. They've either cached it, or they know who to ask to get that question. So let's pretend we haven't cached it, because we probably haven't. So the recursive name server has to do a whole bunch of work now to get this information for you. So the first server they're going to talk to is something called a root name server. So the root name servers sort of live on top of the internet, and at every level, the DNS servers know about the things directly below them. So root name servers know about .com and .biz and things like that. So in this particular case, the root name server doesn't know anything about images.google.com, but sees that you're asking for a .com server, so it tells you to maybe have a conversation with the .com server. So it's going to give you the URL of that name server. So now the recursive name server is going to go talk to the .com server because it was so exciting the first time and we should do this over again. And again, the .com server doesn't actually know about images.google.com, it just knows about google.com. So it's going to tell you that you probably want to talk to a google.com name server, which you're going to do. And at this point, the google.com has an answer for you, knows about images.google.com, and we say that it is authoritative about images.google.com. And it's going to give you back the URL, the IP that you were looking for, and everybody's excited. You have now, congratulations, loaded just the images.google.com page, not any of the styles, any of the JavaScripts on any of your cats. That was exciting. So this doesn't actually happen because this would take hours to get to a cat image, and we want to make cats faster, not slower on the internet. And all of this works because of caching. So all of these name servers will do a lot of caching so that they can minimize the conversations they have. So for example, your recursive name server all the way at the top is going to probably cache all the root name servers and all the .com servers so that it can skip those steps ahead. And every time you ask it a question, it's going to cache that answer. So if I ask it for images.google.com once, the second time I ask it for that, it's already going to know and just spit out the answer. So that's going to be really fast. And the way we know how to cache things, oh no, this is so weird. Okay, the way we know how to cache things is because of the TTL, and that's the time to live. And it's basically how long we can store one of these URL to IP mappings before they get really old and get back pain and we can't use them anymore. If your hosting allows you, for whatever website you have, you can change your TTL. You can make it really small, like a minute or a second. But that's kind of being a jerk to the internet, because that means your DNS has to do a lot of work to load your Justin Bieber webpage, and that's kind of rude. I think the google.com website has about 5 minutes of a TTL. So the caching in the TTL makes the DNS really fast, so it can give you an answer really quickly. But on top of that, we want to also minimize the number of conversations we have with the DNS. So your browsers, I know Chrome does this for sure, Firefox probably does it too. Browsers also have a cache for all of these DNS requests. So if you go in Chrome to that URL, you get a page like this, and that's basically the internal cache of the browser, so that if it knows any of these answers, it's not even going to try to have a conversation with the DNS server to resolve it, it's just going to pull it out from its cache. And you can see that some of them are expired, and you can see that most of them are sort of ad domains. We want to cache all of those, because if we're trying to show you ads, you really don't want to have to talk to a DNS server about all of those. So that's caching, and it makes it really fast. Unfortunately, the problem with TTL, and the reason why it's a pain in the ass, is that you and everybody else in this room have probably a different browser cache, are probably hitting a different DNS server, and that server has a different cache. So that means that if you're updating your hosting, or something changes in your hosting where your IP needs to change, you have to wait for all of these things to update their cache so that everybody sees the same result. So this often happens where you finally published a new blog, and you can see it, and nobody else can see it, and you have little panic attacks. And this is the only useful thing in this talk, and that is whatsmydns.net, which is an amazing website that's basically going to do a whole bunch of work for you. And whatever URL you're going to give it is going to hit something like 50 DNS servers around the world and tell you what they're resolving it to. So then you can sort of see how your new IP is propagating across all of these different DNS servers. And that's exciting. The thing about TTLs and caching, and the other reason why they're a pain in the ass, is that they can also be really problematic for hackers and malware. So one of the biggest problems that we have with DNSs is something called cache poisoning. So now that we have a cache, the goal of all the malware servers around it is to sort of corrupt all of your caches. So if you remember when we were doing this dance, we were talking to that .com server, and the .com server was like, oh, I know about this google.com DNS that you should ask about images.google.com. But let's pretend now that I've somehow, I'm a malware server, and I've somehow managed to convince the .com server that I'm really authoritative about anything in google.com. So I'm pretending to be the google.com name server. So now this recursive name server is going to ask me about images.google.com, but because I'm a malware jerk site, I'm actually going to return a really terrible IP to something that's probably going to install Candy Crush on your computer. And I'm going to do so with a giant TTL so that it basically never leaves that cache. So it has an enormous TTL, so your DNS is going to keep looking at it and be like, yep, Candy Crush is still valid. I should keep responding with this. And this is called cache poisoning. It's really hard to fix because DNS servers don't really have a lot of security. Like, they have security, but it's not a spec. There's a spec for security in DNS, and it's really slow and hard. So, yeah, this is great, cache poisoning. It's a thing that happens. Don't write a DNS server. Cool. So now, at this point, we know how a DNS works. We know how our browser should talk to a DNS. Let's write a DNS server, because that's what we came here for. So our first intuition is to go look at the RFC. Nope. The DNS RFC was written in 1997, has a revision in like 1992 or something like that. It's really long, like every other RFC. It's like 100 pages long and query new. If you put the readability extension on it, it does nothing. It burns your eyes all the time. Do not go read it. Because instead, we have tools. And tools are the greatest because you get to use the command line. Don't let your cat be a DNS server, as a side note. It's not a very good DNS server. Also, all of these are my cat. I have one cat, and I take a lot of pictures of it, like everybody else who has a cat. So I decided that I needed to put them on a slide deck so I can finally use them. Cool. The first tool we're going to talk about is Nslookup. And it's the simplest tool and does exactly that. It looks up a name record for you. Is this too small? Yeah. It is. So if you do Nslookup google.ca, you're going to get a couple of things. It's going to tell you what DNS server it's using, and then it's going to give you the answers that it would get back. So in this case, you can see that it's getting some non-authoritative answers, and there are 5 of them. We're not surprised that they're non-authoritative, because this is the recursive name server that we are originally hitting. And then we get the IPs. And any of these IPs you can put in your browser, and you're going to get to the google.ca page that you really wanted to. It gets a little bit more interesting if you try to nslookup something like notwaldorf.github.io. So that is, that's my blog. It doesn't have that many cats. It has some, mostly these ones. But if we try to nslookup it, we're going to get a really strange answer about how this is a canonical name for like this generic-looking Fastly server. And this is because the IP that we're getting is actually a shared IP. So the way shared IPs work is that there's only a finite number of IPs in the universe, and if we gave each and every one of you an IP, you will make a Justin Bieber blog. I'm Canadian. This is really a problem for our country. So we don't want to waste all of our IPs on Justin Bieber blogs. So the way hosting companies work is that they have a giant server. That giant server has an IP, and then the server knows what to return to you when you're asking for it based on what your HTTP request contains. So in this case, it would see that I'm asking for the Not Waldorf GitHub page, so then it would return that one in particular. So this means that if we're going to the 199.27 URL directly, we're going to get a 404 page, because that's a really generic request, and we're not actually telling that server what we want. The reason why this is important is that if you're writing a DNS server that resolves everything to cats, these cats should live at a static IP, or else you're going to assume that all of these magical HTTP requests are going to have information about it, which are not, because you're probably just trying to check your email, and instead you're going to get cats. So, static IPs. The second tool, and this is my favorite tool in the universe because I have an unfortunate fascination with DNS now, is DIG. And DIG, and I kid you not, stands for Domain Information Groper. Yeah. And it's awesome. And the reason why it's awesome is that if you just use dig and google.ca, you're going to get the entire DNS response for that. And this is why we don't need to read the RFC, because now we know how to parse this message. So the first thing that we're going to get is a header. So the header is, again, this was made in 1980s, so all of these are literally bit fields. They're ones or zeros and nothing else. You can't cast them nicely to anything. So the header is really generic, and it's shared between the question and the response, and it has things like, do you have an error? How many answers am I giving you? Is this authoritative or not? And then we're going to get the question. So if this is a question message where I'm asking a DNS server for something, it's going to say what I'm asking for, and then 2 fields, in and a. A means it's an address record. This could also be a CNAME or a certificate, because you can ask for different things. And in means internet, and I have not seen a request that isn't internet. Other options are chaos, and I don't know what chaos is, but I really want to. And then the answer section basically echoes everything that the question message had, but adds this extra answer section. And this answer section adds exactly those two fields that I told you about. The TTL, which is the 238 seconds there, and the IP of the thing that you're looking for. And that's it. That's our DNS message. Dig gets really exciting if you pass arguments to it. We can pass trace and an actual DNS server that we're wanting to hit. So now I want to hit the public Google one. And trace basically means listen up, recursive name server. Ignore everything that you have in your cache. I want you to do that entire dance when you ask the root server and the TLD and all of those things. So now if we want to look at like fun TTLs, the root name servers, the dot, have something like 4 hours. These are also the servers that are the easiest to hack, so you don't want to give them a giant TTL so that you kind of get screwed for a little bit. And then you have the .com and the Google.com name servers, and these have like 48 hours because they're very unlikely to change. They're very stable IPs. And then when we get the images.google.com, it turns out we don't actually get images.google.com directly. We first get the CNAME, and the CNAME is basically an alias, and it makes maintaining all of these IPs and mappings really easy for the people who own images.google.com. And then we finally get the actual images.google.com. Dig is the greatest. You should all, if you have a Mac, it's already installed, and you can start digging everything, and it's going to be great, and you're going to waste an hour and a half. Cool. So let's look at some Node code, because this is a Node conference, and I'm a C++ developer, so I don't want to talk about compilers, because they hurt my life every day. Yeah, so Hacker News told me once that if I want to be really metal, I should use Node, because that's the thing to do nowadays. So obviously, when I wrote this, I wrote it in Node. Also, I don't speak any Python and Ruby, so this is literally the only language I know how to write a server in. So I did. And it requires 4 glorious packages and nothing else, and it has about 70 lines of code. Dgram is a thing that will make a UDP port for you. Buffer is the thing that comes down the Dgram. Node.bit array is the thing that we're going to use to parse the contents of that buffer into a little bit array, because we need to figure out what we're asking for. And IP is the greatest thing ever, which is going to convert from a string representation of IP to a long, because that's what we need to return in our message. That's it. And the way this actually works is first we're going to create our socket. It's on port 53, so this means it's sudo. So either you start cat DNS as sudo. Cat DNS actually is going to throw away the sudo bit after it's successfully created the socket, because pull requests are awesome. I didn't do that on my own. And then every time we get a message, we're going to do a couple of things. We're going to parse this message so that we can figure out what the browser is actually asking for. And then we're going to massage this question into a response, because most of the fields are the same, except for a couple that you have to flip, and you need to shove that answer field on it. So we're going to add either the cat service IP or the Emger IP, and hold that thought for a second, into the answer. Then you're going to do a little Smither sort of giggle to yourself, because you're now returning cats, and you're going to return some cats to the browser. And now you've ruined everybody's internet experience. So let's talk about Emger. If you remember, cat DNS shows you a picture from Reddit. This picture lives on Emger, and this means that you need to know the actual IP of that image, because otherwise you're going to get into this ridiculous dance where you're asking for Google.com. I'm going to give you the cat DNS, the cat service IP. The cat service IP needs to display an image to you, which lives at Emger. So obviously we're going to resolve Emger to what? To the cat service IP, which needs to display an image to you. So this is not good. So this means that when you actually need to display that cat image, you need to know where that cat image is. So basically, technically, if you go to google.com, you're going to get cats, but if you go to any Emger URL, you're actually going to get that correct Emger URL, because we know how to resolve that correctly by hard coding it, obviously. Cool. So now we know how to get our cats. So we have learned things from here, mostly that you should never write your own DNS, because that's insane, and don't do it in Node, because that's really insane. But most importantly, that your DNS sort of blocks your access to the internet. So that if you have a really shitty and slow DNS, that means that everything on your internet is really slow and shitty. So one thing that you can do is pick a faster one. So if you find that maybe your name server resolution is too slow. So I think in Chrome you actually get a little sad message at the bottom, which is like waiting for name resolution or something like that. So you can try using the Google public one if you want. You can also host your own. So Bind is open source, and you can download it and install it and sort of slap it on a server, and then that's going to be your DNS, and you can use that. Bind is kind of a giant hole of worms, so maybe you don't want to do that. And You can also get around geolocation. So a really exciting pastime of Canadians is to try to watch American Netflix. And one way in which you can do this is to use special DNS addresses that sort of also do a man-in-the-middle proxy, but generally get you to American Netflix. And it's really exciting, because now we have Gilmore Girls. And this also happened in Turkey, I think, if you remember, when the Turkey ISPs were blocking a whole bunch of websites, like Facebook, and then everybody started using 8888 because Google obviously does not block any of these websites. But most importantly, and what I think you should do, because this is my favorite pastime, is you should go on GitHub and download this code and put it on your router so that every time, and open up your router and open up your Wi-Fi so that all of your neighbors can try to connect to your Wi-Fi, and then they're going to get cats instead of their Facebook page, which is amazing. Thank you.